Okay, so when we were discussing different type of input modules, we discussed the analog input module. So when we talk about analog input, we understood that there is an incoming voltage signal. So there is for example, this is my analog input module, and then I have connected this to this particular channel, and this signal is, for example, varying from 0 to 10 volt. And this ADC, which we are talking about, there is an analog to digital converter inside this analog input module. So what I understand from this ADC, that there is an analog input voltage, and this will be correspondingly producing, depending on the number of bit resolution, those many digital values basically coming out over here. So let's say that if this ADC is 8-bit resolution, you're talking about resolution, it means that I will be able to divide the complete range of the voltage, that is 0 to 10 volt. So it is 0, and then the other side it is 10 volt. Then this complete range of the voltages has been divided into 2 raised to power 8 values. That is what we understand. And so when we say 2 raised to power 8, it is 256 values that will be coming up. So if you just divide the complete range by 256, so 10 divided by 256 is something that you will get over here. And so this is the minimum voltage that your ADC can differentiate. It means that this signal is continuous. The signal will be continuous, but the value that will be represented by 8 bits will be in a discrete values, and those discrete values will be basically dividing the whole range of voltage into 256. And same thing is also valid here. So if I am representing this 0 volt with a 0 degree centigrade and 10 with a 100 degree centigrade, for example. So that is the situation. We'll see that here it is 0 to 200 degree centigrade. So now 0 degree centigrade corresponds to 0 volt, 100 degree centigrade corresponds to 10 volt. It means that the full range I will be discretizing depending on the number of bit resolutions. And that is how this happens. So we normally divide by 2 raised to power n minus 1 because we are counting from 0. So it will be 0 to 255. So that way, if you see here, the 8 bit resolution, you just divide the 100 degree centigrade by 256. You will get the value that corresponds to the minimum temperature that you can differentiate. So if I just see that it's roughly coming out 0.4. No, let's see that. I think so. If I just 250, just take 1000 by this, so 4.4. No, is that right? Let me just recheck.
Yes.
So 100 degrees centigrade, if I divide by 256, so certainly it will be coming 0.4 degrees centigrade that you can differentiate. Fine. So now if I want to attempt this, the minimum X bit resolution of ADC, for example, if I apply the same 8-bit ADC here also, then what will happen? So then your the range of the temperature is 200 degrees centigrade, and if I divide by 256, you will be roughly getting around 0.8 or 0.9 something. It means that I want to differentiate between the temperature, which is 0.5 degrees centigrade. So in that case, I have to reduce I have to increase the resolution. Then I have to reduce this discrete values actually. So in that case, what I have to do, I have to just increase one more bit. So if you get 2 raised to power 9 and 2 raised to power 9, you will get to know that it's at 512. And if you divide by 200 by 512, you will be able to get a value which is less than 0.5 degrees centigrade. Right? So our intent is that we should be able to read the minimum voltage that corresponds to the parameter we would like to resolve. And that is something is very important whenever we select the analog input module. The bit resolution is very important parameter here. So there are two important parameters. In fact, the one is the resolution bits. That is what you need to understand, resolution bits. and another is the sampling frequency. So whenever we deal with the analog signals, which are continuously varying signals, these are the two important parameters we need to, and these are the two important specifications of all ADCs. So whenever you are going to select an analog input module, we need to specifically look at these two important specifications. Because depending on your signal you want to resolve, this sensor is not going to make any difference because it's continuously producing 0 to 10 volt. But if my ADC is not able to distinguish between those values, then the limitation is coming from the ADC side. How much is the minimum value that you can read through ADC? So that is the way I think 9-bit will help you in solving this problem. So because with one single bit increase, it will be just discretizing the whole temperature range into the 512 values. And that will bring you certainly less than 0.5. Is this clear?
Yes, sir.
Okay, fine. So we'll continue discussion today. We will be discussing the addressing part in today's class.
Sir,
Yes.
there was another one in which we were to find out the module B, and it was given that it was connected to fan. So the output that the answer reads will be digital. Sir, but there was no mention that there is a knob in the fan or not, so that we can control.
Just a minute. If you remember the question number, that will be helpful. Or what's your name?
Sir, Prasasti.
Prashasti, just a minute. Let me check. The questions that you made.
Question 7, sir.
This is about the analog. Sorry, the modules A, B, C you're talking about, and the outputs were connected. Is that right? And
Yes, sir.
Module B.
And we were to identify the module B, fan which is.
Correct. Yeah, so you mean that you get confused that whether you will be controlling the speed or it is just an on and off function. Is that right?
Yes, sir. It was not given anything, so we just thought that it is a fan. So as we normally see in the fan, so we get
part. Okay. So sorry for that. I think that's a confusion. So just keep it. Doesn't make much difference, but then I will make this kind of questions more clear next time. Yeah. So maybe because of confusion regarding the fan speed, I should have written that you have to on and off the fan. I think that will be more appropriate.
yes, sir. Like in the lamp, it was written that it will be either on or off. But this was not written. Yes.
Okay. Let me see that I will make correction also to this. Anybody attempted differently this question? Anybody have identified that this module B will be the digital output? I'm sure that some of you might have done that.
Yes, sir.
Yes.
Yeah, so I think let's not make correction at this stage because these are the not going to make much difference, and certainly I will take care about the clarity on the question next time.
Yes, sir. Okay.
Fine, thank you. So now we will discuss further after understanding these basic 5 instructions. Let us see this. So this is the architecture of our PLCs in the lab. You have not visited, but you are doing some experiment also. But this is the way we have the whole system in the lab. So we have Micrologic's 1100 PLCs, which are the integrated PLCs with the IOs onto that. And then we also have a compact logics, which is a modular one. So we have both the configurations. So this is your Micrologic's 1100, which is a compact PLC with IOs into that. And we have expanded the PLC capabilities with the two additional analog modules. One is the analog input module, because this PLC comes with the digital inputs and outputs only. If you want to add an analog input to this, it has certain flexibility that you can add on additional modules. So we have added 2 modules. One is the analog input, one is the another analog output. So we have this Micrologic's PLC connected with the terminals here, and we also have this modular PLC basically, which is having additional functionalities, and it has more capability than this standalone or this compact PLCs, because we are able to control the motion, that is the servo motion, with the help of this compact logics. These PLCs may not be able to do the motion control part. So if I am designing a machine where we need to produce a motion, then certainly this will not work. So that is how we call them in a PLCs. And this kind of a system we call it in a PAC, that is a programmable automation controller. So it means that it gives you more flexibility other than just simple logic implementation. So that is how the motion is coming as a part of this. Then we also have a remote IOs basically connected to this PLC. Remote IOs are like that. You can take the IOs away from the PLC. Last time we have seen that whenever we have to connect a pressure sensor, we are looking forward that with the current output, we will be interfacing with a large distance. But in this case, even the distance is much higher. If it is 100 meter or 150 meter, you can use this remote IOs actually. So these are the remote IOs. It means that they are communicating on a different communication bus over here, and then you can interface the sensor directly near the machine. So this module will be mounted near the machine, and then this is a communication bus which is coming to the PLC actually, and through which you can communicate and interface with these IOs. Then we'll also have the variable frequency drive here. So that is a VFD to control the speed of the induction motor. So AC induction motor speed can be controlled with the variable frequency drive. So you can digitally communicate with this VFD. So this system, if you see, you have an IOS, certainly you can interface with the logical input output. But on top of that, you will be able to control the servo motion. So these are the servo motors over here. Then you will be able to interface the IOs at a remote location, that is with the remote IO modules. And then you will have a VFD over here through which you can control the speed of the AC induction motor. So that is the advantage of this kind of modular PLC. Certainly it has an Ethernet module also connected. So each of this, what you are looking at this is an individual module. So this is module to interface with the Ethernet. This is the module to interface with the VFD. This is the module to communicate with the remote IOs. And then you have a servo motion module also. So that way I can have multiple functionalities into the same PLC environment. And then these kind of PLCs are suitable for the machines basically. If you want to implement any kind of a CNC motion control, you can use this kind of PLCs to some extent. Then you also have an HMI over here, that is a human machine interface. We'll discuss later on. It's a very important part of each machine, that how the operator will interact with the machine. So operator normally interact with the push buttons, interfaces like indicators or the control switches. These are the conventional ways. But today you will find that the computers are so low cost that you can interface the machine with a dedicated computing environment. So this will be having a touch panel with a color screen, and then you have some push buttons onto that. So this HMI will serve the purpose to get a visualization into the system, what is happening inside the machine. Otherwise, you can't see anything, what is happening, how the IOs are executing. You can't see anything here. Only with the human machine interface, this kind of panels you can use through which you can visualize what is going on in the system. Then you will have systems with programming environment. That is what the RS logics we are using. So you can develop the operating stations here. So here you can just use the logic part, you build the program, and finally you can download that into the individual PLCs. Because all PLCs are on the network, so you will be having some IP address to all the PLCs like this. So you have IP address, and whenever you build the program, and you will be downloading on a specific PLC identified with the IP address. And that's how in the lab you can download the program on any of the PLCs, because they are all interconnected on the Ethernet. So this is just a depiction of the environment that you'll come across in industry, how the communication and connectivity work over the Ethernet. So these are the ways you can see that how the panels are wired here. I was explaining the PLC panel. So same way we have that in the lab. So this is the PLC, and then you have the circuit breakers over here, and then we have screw terminals basically, that you are not supposed to connect the wires directly to the PLC IOs. These IOs are terminated into these screw terminals here, so that you can interface your sensors devices to the screw terminals, and rest is the power supply over here. Connections, if you see here, you will come across. I'm just giving you this information for a practical understanding, because theoretically, certainly you understand. I have just drawn a block diagram and shown you the terminals over there. But physically, when you come across, because you are not doing lab physically as such, but anytime whenever you have an access to the PLC, you have to look at the connection diagram, or I should say the instruction manual of the PLC, and through which you will be able to see how is the pin configuration inside the PLC. So if you can look at this pin configuration, this is how the PLC looks like. So if you see here, you have IOs. So I0, I1, I2, I3, I4, 5, 6, 7, 8, 9. It means that you have 10 digital inputs over here. So that is most important part to understand. So which pin you have, the IOs are terminating here. So IO0, I1, I2, I3. And so you have 10 digital inputs. And then you have 6 digital outputs. So O0, O1, O2, O3, O4, and O5. These are the 6 digital outputs. So these are the inbuilt IOs into the PLC, that is Micrologix 1100. So you can interface 10 digital inputs, and you can control the 6 digital outputs through this PLC. And rest is the programming that you are supposed to do. Apart from that, this PLC also have certain plus 24 volt terminals here. So you can see that plus 24 volt DC, plus 24 volt DC. Then you also have a common, that is the ground terminal over here. So DC common is there, and that's all. So now in this case, what you can see on the other side also, you have a output terminal, and then you'll also be having a ground terminal over there. What I just want to add over here, we normally isolate the digital outputs. Inputs are fine because your inputs are coming, or you can also use a relay for isolation over here. So isolation through relay is a very important implementation in all automation systems. Isolation. When I say isolation, means that I don't want any of the wrong signal will enter into the PLC and it will damage. And this, when wrong signal, when I say either it's an over voltage or the short circuit, something happening outside with the device, it should not be damaging the PLC inside it. So that is how the isolation works. And isolation is done with the help of a electromagnetic relays actually. So that is the component that you need to understand. So in an electromagnetic relay, let me quickly draw and then show you here itself. Let me just draw it. So electromagnetic relay is like this. So you have coil terminals like this. So there's a coil here inside the, it says an electromagnet with a coil. So these are the coil terminals we call A1, A2. And then there is an armature basically, which is floating here with the additional terminals, which we call contacts basically. So you have 1 and 2, these are the contacts. And with the mechanical spring, so you have a mechanical spring. So this is the coil and this is a mechanical spring, which will keep this in contact or in touch with one of the terminal. So if you see here, I will be adding a wire here. So this is one wire which is common. And then you will be having 2 more wires here. So 1 and 2 like this. So this is basically known as normally closed, and this is known as normally open. So these 3 are the electrical terminals on this relay. So this relay is having electrical terminals, and then this coil terminals over here, that's A1 and A2. So these 3 contacts are there, and A1, A2 are the coil basically here. And you can see that this A1, A2 is completely galvanically isolated. When we say galvanically isolated, means there is no physical wire connecting A1, A2 side of the circuit with the contact side of the circuit. It means the NO, NC common. They have nothing to do with the electrical connection on the A1, A2 side. So what is the advantage of the, and this complete unit is housed inside a box, a small unit, that is what we call the relay. Now let's try to understand the functionality over here. When the current is not flowing into A1, A2, it means that there is no current in the coil. What will happen? Because of the spring force, your common is connected with the 2, that is normally closed terminal. So if anything you have connected between common and NC, it will be getting a continuity. So that if you can see that if you supply a voltage to that, then your device will be on. So that way, when there is no current into the coil terminal A1, A2, then the common is connected with NC. And when I make the current flowing into the A1, A2, then what will happen? Then this magnet will pull out this armature towards it and against the spring force, and then this will get connected with the 1. So COM will get connected with the 1. So if you see here, whenever there is no current in the coil, so if I just want to draw this table here, this is a coil here. And if I say this is common terminal, so when there is no current, so 0 amperes, let's say that there is no current inside the coil, then what is the connection here? This COM is connected with the NC. And whenever I make the, for example, 1 ampere current flowing, and that is possible when you apply the voltage to this coil here. So once 1 ampere current is flowing in the coil, then COM is basically connected with the NO. And that is how the changeover will happen. So, and any device which is connected between the COM and NC or NO, it will be actuated or it will be operated with the help of the current in the coil A1, A2. Now, if you see, as I was mentioning, there is the complete isolation between the A1, A2 terminals. So A1, A2 terminal is supposed to operate at 24 volt DC. That is what the PLC can produce. But this connection to the COM, NC and NO could be any voltage. It has nothing to do with the 24 volt DCs. For example, if I am willing to control the fan, which we were discussing. So if you have an AC fan and I would like to control that AC fan with the this relay, then what I will do, I will be having connections made like a switch over here. This is almost like a switch here. This is an electromagnetic switch, and you will be operating 230 volt AC on the other side. So your fan with the 230 volt AC connection is connected between the COM and the NO connection, and then you will be having a fan connected. So load will be of 230 volt AC in this case. Now, if I'm supposed to make the fan on and off with my PLC, so fan is now supposed to operate at 230 volt AC, but my PLC is producing only 24 volt. So in that case, I will be preferring to use this relay. So PLC will be energizing the relay only, and through the contacts, I will be able to make the fan or the load on and off. So that is how the isolation works very well over here. One is in terms of the voltage that you can see over here. Otherwise, you can also use these relays for the inputs also. Otherwise, you can't control the AC load with the PLC. Without relay or without contactors, you can't control the any kind of a load with the PLC, because your PLC will be just giving you 24 volt DC, and certainly the current is also very less. Current is also very less. So that is the part you need to see. So with this kind of a isolation, we normally connect the relay. So if you can see here, the output relay is connected over here. So this O0 is now going into the relay. This is a relay 01 coil. So we are just drawing the coil over here because PLC is only controlling the coil. So other side of the coil is grounded. That is how it has been connected to the common. So whenever 24 volt DC is available on this terminal and ground is already connected, this coil will be on and energized, and then it will make the contacts operating for this relay. So we have 6 relays over here, and which is responsible for controlling any of the 6 loads that can be connected over here. So I'm sure that you have understood the basic of this relay. Normally we teach relay in detail in the automation courses, but just for a quick understanding, I have explained the relay, and I'm sure that you have understood this functionality of the relay. Anybody who has not understood, please let me know. I can explain it again. Fine. So if the relay is clear to you, I think that is the way we are supposed to control the load from the PLCs. Fine. Now, when it comes to the analog input output modules, because that is the additional modules added to this PLC. So analog input module is there. So you can have this channel 1, channel 2, and channel 3. So 0, 1, 2, 3. So this is the 4 channel. 4 channel analog input module, and this would be the 10-bit ADC here. So if you can see 4 channel analog input module signal, but this is having a 4 to 20 milliampere signal. So that's how you can have module with the 0 to 10 volt DC also. This is just a catalog number for this particular. So that way you have analog input module, you have analog output module over here. And this is what we call the potential free contacts. In the relay, the contacts that I have explained you on the other side, that is common, NO and NC, these are the potential free contact. It means that there's no potential on this contact. There's no voltage onto that contact. So you can use them as a switch. So that is how this contact that you can see here, this is the contact of a relay 1 only, and this is the contact for the relay 2. And I can connect any of the load over here. So if I want to operate a fan, for example, so if you see here, let me just draw that. So if I am supposed to operate a fan, what I will do, this is your AC signal, 230 volt AC. And what I will do, I will just connect the fan like this. So what you have done here, so if you can see that the one wire of the 230 volt AC I have directly connected to the fan. Another terminal is coming through this relay. So if you see here, this wire is now going into this relay, and the other contact is basically coming to this fan. It means this, if relay contact is open, the fan will not be getting 230 volt AC. Only when the relay contact is closed, then the fan will be getting 230 volt AC, and then it will be able to run. So this is the way you will be connecting the load to these relay contacts outside the PLC. And then you will be able to control. So maybe it's a heater that you want to control, it's a fan you want to control, or some other device you want to control. Now let's go into the detail. This is just an UI interface. The most important part is the addressing, though you might have started implementing the addressing in the lab. But let me just explain this. This is a very important part. Once we understand the IO interfaces to the PLC, the second thing, how you will be telling your program which input or which output you are talking about in the program. And that is coming through the addressing. So when I say addressing, it's almost like the address we normally use for telling someone to go at a particular place. So if I ask you to go to, for example, Aman's home, certainly without address, the first question that you will ask is what is the address, and how to reach that will come later on. So address means basically, first of all, you will define the country, then you will define the state, then you define the city, then you will define even the within the city will not also be. If I ask that is house in Delhi, doesn't make much difference actually. You can't understand where in Delhi actually. So unless you will tell the colony name or the block where he is living, and then within that colony also again that will not work unless you pinpoint the exact house number. You got that? So for address, if you see that how you have traced it, start from the country, you go to the state, go to the city, go to the particular colony or mohalla, and then particularly you will be then knowing the house number is the final destination, then only you will be able to reach. So house number in the addressing in PLC is the bit, that is the last destination you want to reach. So all the IOs are basically read by the PLCs, and these IOs are arranged in the form of memory bits, or there are memory inside the PLC which will be storing the state of this IOs. So for example, if you talk about the 16-bit PLC, so then you will be having in a 16-bit location inside it. So let me just explain it with the 8-bit, then we will talk about the 16-bit. So 0 to 7, these are the 8 bits, and this is called as a memory register. So memory inside the PLC is arranged in the form of memory registers, and then each location is storing the state of one single bit here. So this inside the physical memory inside the PLC, it has to be mapped with the physical interface on the PLC. So for example, you have seen there is a digital input physically located onto the PLC terminal. This digital input has some mapping inside the memory, and this mapping is accessible through this addressing mechanism. Fine. So before I come to the address, we'll quickly understand this file structure basically inside the PLC. So the data inside the PLC is organized in the different type of files, as we normally organize the cabinet with the files in office. So same way you can visualize this. So there are two type of file. One is the data file over here. One is the data files. Another is the program files. So data file is dealing with the data that is stored in the RAM, and program files deal with the program that you will be writing. So finally, whenever you write the ladder logic and you compile the program, build the program, and you will be transferring this program into the PLC. So this program will go inside the program files. Whenever you compile and build a program, and this binary data which is representing a logic program has to go somewhere inside the PLC, and that location is the program files. So program files, again, there are a few type of files which we are not directly writing. So there are two system files, system file 0 and system file 1. If you can see here, system file 0, system file 1. You're not supposed to do anything with this system file. Your program, whatever you will be transferring, will be written into the program file 2. So your first program, and there's only one program basically at any point of time inside the PLC. So you can't have multiple programs inside the PLC. At any point of time, there is only one program running inside the PLC. And this main program will be residing in the program file 2. Now, still there's a space for program files 3 to 255. And this space is mainly reserved for writing subroutines. So you can have a main program and there are sub-programs basically. That's how we normally organize the program in this way. You have a main routine and then you have a subroutines. And you will be calling these subroutines or sub-programs in the main programs multiple times. So that way your main program is residing in program file 2 and the rest of the sub-programs will be residing in the program file 3 to 255. So that is how the program is stored inside the PLC. Next comes the data actually. So there are identification of these data files. They should be organized in some fashion. So that is how the identification has been made for this different file. So one is the file type. So there are different type of files in which you want to keep different type of data. So if you can see here, there's an output file, there's an input file, there's a status file, bit file, timer file, counter file, control file, integer file, floating point file. So these are the different files. And then after, so 0 to 8, this file type is fixed. That's a very important point to understand. 0 to 8, if you see here, these 9 files are fixed actually. You can't change them. You can't have 0 as a bit file or you can't have a 1 as a status file. That can't happen. So PLC by design itself have these 9 files type are fixed actually in this case. Only you have a flexibility to extend these files. So after 9 to 255, these file numbers, you can define any type of file. So bit file, timer, counter, but still you can't have them in an input output file. Please note that. So input output status, these files cannot be created again. So they are the only fixed files over here. So all your information related to the PLC status, input and output, they will be written and read from these 3 files only. Only you will be able to create the data files like bit file, timer, counter. They can be created multiple files and you can have till 255. So that is how the data files are organized. So once you understand there's a file type and then there's a file number. So if you can see that this is an output file, you can see that this is an output file and file number is 0. This is your input file and file number is 1. This is a status file and file number is 2. Bit file, file number 3. Timer file, file number 4. Counter file, file number 5, and so on. Now it's possible that I can have a timer file that's T4. That is timer and 4, file number 4. So I'll write the file type and then I will write the file number. I can easily write T9. So timer file with file number 9. So that means that I have created one more timer file here from 9 to 255. I can't have this I10. This can't be possible because I have only one input file and that input file is I1 and your output file is O0. So if you can see that this is your output file O0, this is your input file, and each file is having memory registers, what I was just explaining. So each file is having multiple memory registers. And because this is a 16-bit PLC, this is then a 16-bit PLC. So each memory register is 16-bit long. So each memory register, it means that I have to address. So if you see that I have to reach to a bit location inside the memory register. So the address, as I was explaining, how you will reach out to that address. So first of all, you will identify the file type, then you will identify the file number, and then within that file type, file number, you have to reach out to the file register, basically which register, because each file will be having multiple registers. The way you can see that there's a page, and then on that page you will be having multiple lines. So that is how the registers are also organized. So memory registers are there. And then once you reach out to the register, then in that particular register, which bit you are trying to address. So that is the way you will be addressing any of the bit inside these files. And that is how the addressing come into picture. So please understand and check that which is the correct file number or file type possible and which is not the possible file type and file number. Once you understand this, then we'll come to this addressing. Now, whenever we want to locate or address a memory inside the PLC, this is the way you will be addressing. The first number that is coming as a file type, or the alphabet that you will be using is coming as a file type. So this X denote the file type over here. So if you can see here, this is your file type. Fine. Then you will be going to the second number, which is a data file number. So once you have a file type identified, then second is the data file number. That is what I was just explaining here. So you have file type and file number. So these first alphabet and the number represents the file type and file number. Then you will be placing a colon over here, which is known as slot delimiter. So if you can see here, it's in a slot delimiter here. It means that after that I have to mention the slot number. And what exactly this slot is? Slot is something how you will be addressing the IOs or the memory inside the PLC. And it's more related with the slots for the IOs, the input and output. So when I say slot 0, it means that I will be addressing the IOs which are embedded into the PLC. Fine. So slot 0 is what is representing the IO modules which are directly embedded into the PLC. And whenever we will be expanding the additional IO modules, then they will be identified as slot 1, slot 2, and slot 3, and slot 4, and so on. Fine. This is very important because if I will be writing or if I will be reading the bit 0, then it is important to communicate that bit 0 of which input module. Is it the embedded input module you will be talking about, or it is or is it an expanded module that you will be talking about? So bit 0 could be possible in multiple modules. So that is the important part over here. So if you see here, it is written here also that IO located on the controller, that is embedded IO, is slot 0, and IO located to the controller, that is expansion IO, begins with the slot 1. So you can have slot 1, 2, and so on. And that's how the modules can. So slot number will be there, and by default, because we will be mostly addressing the IOs on the PLC, we'll use 0 over here. But there's a possibility that because in the previous module we have previous PLC we have expanded with the 2 additional modules, analog input module and analog output module. So they will be going into different slots, slot 1, slot 2, and so on. Now with the slot, now within that file, now I will be coming to the word actually, and word is basically 16-bit. As I was saying, these are the 16-bit memory registers. So each memory register is designated as one word. So each 16-bit memory register is known as one word, and within the word, then I will be talking about the bit. So then you will come to the word number over here, and after that you'll put a slash, which is the delimiter for the bit. So within that word, which bit you are talking about, right? So then slash B. So let's take an example and then you will understand now. So once I have a 16-bit memory register here. So I will just put the name 0 to 15. So 0, 1, 2, 3, 4, and so on. So that way, if I have to basically address this particular location, I want to address this, and this is, let's take that this is an input file. So this input file, I have to address this particular bit 4 here. Now how I will go about the addressing, let's discuss. So what is the first thing that I should write for the address? Anyone in the class?
File type.
File type. So what should be that file type here? What is the alphabet that I use? I, correct. So the first address that I will write I here, the first alphabet in the address. Then because this is in a default input file type, so number is 1. So I1. I1 is known because there is only one input file type, so I can have I, and then there's a, sometimes it is optional also, but for input and output, because there is only one file, so I will be, but let's use the convention to write it compulsory. So I1 will be the file type and file number. Then I will be placing the colon over here, which is a slot delimiter. And we will be addressing the inputs which are directly onto the PLC. So then I will be adding a 0 over here, which is a slot number over here. So I1 colon 0. So I will be addressing the IOs onto the PLC directly. Then it comes the dot, and then because if your IOs on the PLC is within 16, then it means that the digital input information for 16 digital inputs I can easily store in one word. So one word is good enough to store the state of 16 digital inputs, and this PLC which we are talking is only having a 10 digital input. So one word is good enough to store the state of all digital inputs in this case. So 0 dot and then word 0, because we'll be starting with the word 0 only. So 0.0. So this is a slot and this is your word. Slot and this is your word. So we reach out to this location. So if you see here, I'm able to reach out to this word. This is a word which is a 16-bit long inside the input file, and the file number is 1. So I1 colon 0.0. I have reached out to this word location. Now within this word, I have to address this bit 4. So then I will be placing a bit delimiter that I will place a slash. So whenever you add slash, it means you are now talking about the particular bit, individual bit over here, and then I will write the number 4. So this address is basically now address of this particular bit here. If I would not have written this /4, then I will be talking about this complete register. And which is again useful when we talk about the analog inputs, because analog input we will not be talking about the bits. We will be talking about the complete register, because we will be storing 10-bit, 12-bit, 16-bit value inside this register. So their memory addressing will be till up to 0.0. That is good enough, because I will be talking about a complete word over there. But when we want to go deep inside the word to a particular bit location, then we will place /4. Is this addressing clear?
Sir?
Yes.
Sir, can you explain, sir, why you have written 0 for the word?
Yeah, so in a file, so for example, what I was just explaining, once we reach out to the file, so you have an input file. Let's say that you have an input file. So this input file is like this. So this is a kind of a page that you have. And inside input file, you will be having words basically. So then this is one word. Memory is organized like this. So you have another word here. And then this, so memory paging happens like this. So each page is having multiple words. So this is 16-bit. This is another 16-bit here. And this is a 16-bit. So input file will be having multiple words inside it, depending on the size and depending on the PLC configuration. Here you will see that it starts from the word 0 here. This is word 0, this is word 1, this is word 2, and this is word 3, and so on, depending on this. As I was mentioning, because our PLC may not be having more than 16 digital inputs. If I'm just talking about 16 DIs, I can easily store the state of all 16 DIs in one single word. It means that my word 0 is good enough to store the state of 16 digital inputs here. So I will be only utilizing the word 0. There is no need to go to the, if I will be talking about 32 DIs actually. Now let's see that example of 32 DIs. Now, if there is a module where you will be having 32 digital inputs, then certainly you can't span in one single register. The 13 digital inputs are being stored in the two words here. So first 0 to 15 will go over here. Memory will be again 0 to 15. Please understand this, but then I will be talking about the word 1. You got this point? So word 0 will be using the 0 to 15 bits. Word 1 will be having a 0 to 15 again, but I will be utilizing these two words to map my 32 digital inputs. Is this clear?
Okay, sir, I understand.
So let me just, no, this is very important to understand. If I will be talking about 32 digital inputs and how the data about these 32 digital inputs will be read from the memory register. So what I will be having one word, which is word 0. Let's see that. And I will be having another word, which is again W1, right? So then this is 0 to 15. And again, this is 0 to 15. Now, if I have to, so 16 DIs will be mapped over here and 16 DIs will be mapped over here. That is how the 32 bits will be addressed in this case. And this is all belongs to the input file. Fine. Now, if I have to read the 17th digital input, let's see that 17th DI. Now PLC is having 32 digital inputs. I would like to read the 17th digital input. Let's see that what you understood. Let's write the address for the 17th digital input. Can anyone tell that? So I will be starting with the I only. I1, fine, colon 0 slot, fine. Now what should be the word here?
.1.
Yes, that's the point. So we will be now addressing word 1, and because we will be talking, this is the 17th DI. And then I will be placing /0. So this is the address for reading the 17th digital input. So you should be able to find out from these memory registers. If I ask you to read the 24th digital input, you should be able to write the correct address for that. It may not be utilized multiple times. It's not so common, but at least we should understand that most of the time we end up in understanding from that 16 digital inputs itself. Not more than 16 digital inputs required. And if it is, for example, I'm just talking about this 32 digital inputs on the slot 0 itself. It means that my PLC is embedded with the 16 digital input interfaces, right? For example, let's talk about the expansion module. I will be now adding the additional module in the slot 1. This is another DI, and which is again 16-bit, 16 channel, I should say the 16 channel. So 16 channel additional digital input is added. The PLC functionality has been expanded by 16 more digital inputs. Now, how you will address the bit, for example, the terminal 0 here. Bit 0 of this. So again, the addressing will go like this: I1 colon. Now slot is 1 because I will be talking about the 0 bit of the extended module, which is in the slot 1. So I1 colon 1, that is slot, but I will be talking about the word 0 of this slot. And then I will be talking about the bit 0 of this slot. So this is now getting mapped. So this is something which is now mapped to this. So slot and word, these are the two important things you need to understand. Rest I1 will always remain as I1 because that is the digital, this is the input file number. But how the slot number and word will make a difference, which IO, because as I was saying, there is a input 0 over here. There's an input 0 over here. There's an input 0 over here also. So input is always connected to the terminal 0. But then where? Is it on the embedded module or is it on the extended slot? That is first thing, so that the slot number will be decided. And within that slot, whether it is within the 16-bit or it is expanding beyond the 16-bit, it's spanning onto the second word actually. That is how the IO which are beyond 16 will be added over here. So 17 to 31 will be falling into the second word actually. And that is how it has been added. So all start with the word 0 only. All memory start with the 0 bit, and then it is going up to the 15 and so on. I hope this is clear to all of you. So this is something very important in addressing when we talk about addressing and a memory inside the PLC. Whenever you write a instruction that is examine if close. Now examine if close is something you want to communicate or you want to act upon. But where exactly you will be examining? It is almost like that I will ask you to go to someone else's home, but then without telling where the home is. So that's how the address is very important. So same way, if I write an instruction, examine if close, PLC will ask which input to examine. And then you will be writing an address onto that instruction. So instruction along with the address make a complete sense. Right? And that is how the PLC ladder will be written along with the instructions and with the addresses only. Then only the PLC will be able to execute your program, and it will keep reading and writing those memory locations and acting upon and will be executing the logic that you have written. Fine, I think that is how the input output addressing should be done. So there are a lot of examples. So we'll not be starting timer counter in the class today, but certainly the possibility that you will get to run these timer counter in the lab. So then next class we will discuss on these timers and counters. So with addressing and the IO, I think you have an ample understanding to do the lab problems. And today's lab problem, you have to build your own logic based on the and or understanding. You have to combine those input and outputs and make the program running. And that is how it has been planned. So thank you so much. If you have any doubt, let me know. Or otherwise also, if you have any doubt, you can just post on the WhatsApp group also. I can respond there. That is also possible. Any question that you find you want to address, for example, in the quiz itself, you come across anything that is, so after the quiz, don't share anything during the quiz itself.